Bengtsson. Ingemar, please, do you want to share your screen?
I'm trying to do that, yes. Okay.
Okay, please, go ahead.
Just, right, so I will talk about something that I refer to as Sics, which is sort of short for symmetric informationally complete positive operator valued measure, which is a language used in quantum information theory for these things. So you can see why I want an abbreviation. People in signal processing are also sort of interested in these objects. They call them equiangular tight frames, which is a rather nice name. So I'll define them, I hope. That's interesting. How do I? Yeah. So here is a definition of an equiangular tight frame. So you're in a finite dimensional Hilbert space. Dimension D, you have n unit vectors, and you insist that they form a resolution of the identity, some number here. You also insist that all their scalar products have the same absolute value squared. It's easy to prove from this what these numbers have to be. It's also quite easy to show that the minimum number of vectors you need to get the resolution of the identity is equal to the dimension, of course. And the maximum, there will also be a maximum number of vectors you can pack in given that condition, and that is equal to d squared. So we have minimal equiangular tight frames. They are also known as orthonormal bases, and you know they are very important. And then there are maximal equiangular tight frames. These are the things I refer to as Sics. And obviously I'm sort of hoping that these will be very important too. We'll see. They, unlike orthonormal bases, they are not so easy to find. However, it was conjectured quite some time ago by now, first by Gerhard Sauner and then by Renes and his collaborators, that Sics do exist in every dimension and that they are orbits under the Weil-Heisenberg group, which is a finite group that you all know, I suppose. The order of the generators of the group are equal to D, and they obey this relation here, and omega commutes with everything. And Hermann Weil proved that, so you can represent the omega basically by a primitive root of unity. We choose this one, this holds from now on. And then the irreps are unique. And then I have a little quote here. All authorities seem to be agreed that at, or nearly at, the root of everything in the physical world lies the mystic formula, etc. That's actually a quote from Eddington, and it refers to the continuous Heisenberg group, the one that Weil was trying to make a discrete version of here. And I just like this quote. What I'm trying to say is that if you have these groups on your side, then probably what you do is not altogether wasted. These are important groups. One of the properties that this group has is that it is a unitary operator basis. That's very important. Nice error basis, I sometimes call. That means that every orbit of this group is a tight frame, so you don't have to worry about that condition. It's customary in the field to use as the elements of that unitary operator basis these particular phase factors here. So there are d squared elements in the unitary operator basis. This phase factor is a little bit funny. It's usually defined as minus e to the I pi over d. Now that's a primitive dth root of unity actually if d is odd. If d is even, it's actually a 2 dth root of unity. So we're actually extending the center of the group a little bit in doing this maneuver. But if you do it, then you find that the group law takes a very nice form. If you think of these integers here as labeling the points of a little discrete phase space, then you find a symplectic form appearing in the group law. And that makes it easy to define the Clifford group, which by definition is the normalizer of the Weil-Heisenberg group in the group of unitaries. So it's a group that permutes the elements of the Weil-Heisenberg group. And this group will contain, because of the appearance of the symplectic form here, will contain a copy of the symplectic group SL2 over the integers modulo d. Or actually it says modulo d bar. That has to do with this complication in even dimensions, so I should comment on that. It's a funny fact that the Clifford group is harder, significantly harder to understand in even dimensions, basically because arithmetic modulo 2d turns out then. That's at the moment just a fact of life. There's a simplifying feature of the Weil-Heisenberg group that I want to draw your attention to, which is that if the dimension is composite, and if the factors are relatively prime, then the group splits as a direct product. Conversely, if the factors are not relatively prime, then you have two different discrete Heisenberg groups. So this group here is not equal to this one. And I'm well aware that most of the audience prefer this group, which is the one usually used in quantum computing. But people in signal processing actually typically prefer this group. This has to do with the fact that physicists always break things down into atoms, and in signal processing you don't do that. It's this group that has to do with Sics. That's another fact of life. I should also say, concerning the first point about even dimensions, that I somehow feel that the last word on even dimensions hasn't been said yet. I think one can simplify the story, but it hasn't been done. So now the question is if these exist, and I'm going to assume that they are formed as orbits under the Weil-Heisenberg group. So what you do is that you try to find a fiducial vector such that when you act on it with the d squared displacement operators here, you obtain d squared vectors and they should form a Sic. So the equation you have to solve is this one for d squared vectors, for d squared choices here. So this is a set of equations that you have to solve. And that's very hard. People have, of course, looked for these things numerically, and by now, well, people, it's mostly Andrew Scott, actually. And Andrew Scott has found solutions in every dimension up to 193, and in some higher dimensions, the record at the moment is 2,208. More important, perhaps, Andrew is confident that he has found every Sic in dimension up to 50, or 87 if you add a little conjecture. Here I should make a small disclaimer. So what is being looked for here are always Sics that are generated as orbits under the Weil-Heisenberg groups. You could imagine that there are other examples not generated in this way. In fact, in dimension 8, there is one. My suspicion is that that's the only counterexample, but that is not particularly well established. And doesn't matter. From now on, when I talk about Sics, I mean things generated by the Weil-Heisenberg group. Now, when you look at the list of these numerically generated Sics, you find one quite surprising feature, which is that every Sic vector found, in the sense just used, every Sic vector found is left invariant by a Clifford transformation of order 3. This was actually conjectured, it was slightly sharpened afterward, but basically Sauner conjectured that already in the previous century. And Andrew Scott has verified this up to dimension 50. So it seems to hold. And for quite a long time, this curious property here was really the only hint that there is something interesting mathematically about these things. It's still unexplained why this happens. It was also found that there are special sequences of dimensions, presumably infinite, but of course we don't know that. But there seem to be special sequences of dimensions in which some of the Sics have higher symmetry than order 3. This was first observed by Scott and Grassel in a serious way. This also explains why there are some high dimensions where Sics have been found. So when Andrew Scott and Marcus Grassel looked for this particular Sic, they were already confident that there would be a Sic in that dimension which has an anti-unitary symmetry of order 48. That restricts the search space, and they actually managed to find it. Okay. So now we look at, we should look at exact solutions. And at the moment, so this actually I checked with Marcus Grassel the day before yesterday. So this is the latest update. At the moment, exact solutions have been found in 102 dimensions, including every dimension up to something, etc. The world record at the moment is 1,299. And you may wonder what they look like. So actually in dimension 2 and 3, it's easy to find them. There's a very elegant paper by Otto Hesse from 1844, where he made very interesting study of the Sic in dimension 3. But in higher dimensions, they're quite hard to find. So I'll give you an example. And for this, I have to do a little thing here. Whoops. I don't have to rotate things. So what I'm going to show you is something from a paper by myself, although the calculation is certainly not by myself. It's by Marcus Grassel. So we looked for a Sic in dimension 28, where we have some simplifying features. So we need to find 28 numbers here that are the components of the fiducial vector. And there are some preliminaries here. So this was a calculation requiring whatever 45 gigabytes of memory and modular Grödner bases, etc., etc. And using these tricks, Marcus was able to find a number field containing funny things here, square roots of various numbers, also the roots of 2 cubic polynomials. These numbers are all defined here. And then one can write down these 28 components. And here's the first component. Then it sort of goes on. Here are a few more components, and here are a few more components. And very optimistically, we submitted this to a journal, but the journal refused to print this part. The important part of the thing is actually this thing here, the square root of 29. I'll explain why in a second. But I have to rotate things again. Since there's clearly some number theory going on here, we should remind ourselves perhaps about a somewhat similar problem, which is the problem of, I wish this thing wasn't here, but I don't quite know how to get rid of it. Whoops. Well, I don't know how to get rid of this green thing, but never mind. If you look for regular polygons in a plane, then of course you're confident that these things exist. They're generated by a group, just like Sics. But if you want to have explicit expressions for where these corners actually sit, you have to bring in quite horrible things. So there are cube roots and square roots and all sorts of things. So the x coordinate of this corner here, this is at 1, 0, is a pretty horrible expression. Of course, we all know that in the end, it's not really so horrible, because what you can do is that you can define a transcendental function here, or the exponential function. And then you can get the position of these things in the complex plane by evaluating that function at rational points. So then it's all very simple. These are the seventh roots of unity in this case. And I should draw your attention to the fact that the appearance of the exponential function here shows that this problem here is actually an extremely important one. Our modern civilization wouldn't account for much if we hadn't invented the exponential function, which comes out of this problem. So this was a very important problem, very forward-looking. If we think a bit more about this example, things become even more strange, because these numbers here, the roots of unity, if you don't know about the exponential function, what you can do is that you can express them as roots of a certain polynomial, in this case, the sextic polynomial. And we know that in general, sextic polynomials don't admit roots. I mean, don't admit roots that you can obtain just by root extractions like this. But this one does. And the question is why? And this question was answered by Galois long ago. It's because there's a group commuting the polynomial, the roots, keeping the coefficients fixed. That group is actually abelian, and that means that solutions by root extraction are possible. I'll say a little bit more about this stuff here. So Kronecker and Weber proved an important theorem about such things. They found that every number field which has an abelian Galois group over the rationals is actually a subfield of one of the cyclotomic fields. They're called Ray class fields for some reason, which is what you get by extending the rationals by adding an nth root of unity. Every one of these simple fields is a subfield of one of those. Then Kronecker and a long list of people, ending with Takagi, I think, were able to do a generalization of this. They were interested in, instead of using the rational numbers, you first extend the rational numbers by adding the square root of a negative integer, here called capital B. And then they asked for an analogous description for number fields that have abelian Galois groups over this base field. And they were able to solve that problem completely. In particular, they were able to find analogous transcendental functions that give the generators of all these fields, and they were able to find systematically Ray class fields for these things, etc. Hilbert was very impressed by that, so he proposed the problem to find an analogous description of this one, this time for abelian extensions over arbitrary base fields. This proved very hard. So in the 120 years that have passed since then, people have been working on the first open case, which is if the base field is a real quadratic field. So instead of a negative integer, you have a positive integer as a base field. And after 120 years, mathematicians have been able to classify the analogous Ray class fields here, and there are algorithms that you can access on computer programs that allow you to construct these things. But what is totally missing is an elegant description, some sort of analytic description of the generators. So the problem is open. The reason why I put quotation marks here is that algebraic number theory is a rather difficult subject to get into. The quotation marks here means that I don't really understand these things at all. But the nice thing is that you can create these things using magma case by case. So you, after a while, you get somewhat familiar with them, and then they're less scary. I still don't really understand the construction. So, and now we can go back to Sics. Now comes, so to say, the turning point of my story, which begins in 2013, when Marcus Appleby and his collaborators, they analyzed the exact solutions available at the time. There were, I think, slightly less than 20 or something. And they found that every Sic in any dimension D, small d, was actually using a number field which is an abelian extension precisely of a real quadratic field, where the real quadratic field, square root of some positive integer, that positive integer is the square-free part of this number here, d plus 1 times d minus 3. So there is some sort of systematics here. And a few years later, so Appleby, Flamia, McConnell, and Yard, this is a real turning point, I think. They again, by analyzing the available exact solutions, they concluded that at least for the available exact solutions, the number field can be completely specified, or almost. It's a Ray class field over this real quadratic field with conductor D. So D is a dimension in Hilbert space, but it also plays a role of specifying what particular Ray class field you're using. And the Ray class field is always over this real quadratic field where this integer is determined in this way. Actually, in most dimensions, there are several Sics. And for most of them, or for many of them, you will need an abelian extension of the Ray class field. But there is always in every dimension, the hypothesis is that every dimension does contain a Sic, which uses only this Ray class. That's a game changer in two senses. It's a game changer because it connects the problem to something completely different, which is also important. It's also a game changer because suddenly we know what number field to use. I mentioned that by now 102 dimensions we have solutions in 102 dimensions, not only the roughly 20 that are available to these authors. The conjecture holds. It's always this number field. So it seems quite solid. So I'm going to say a little bit more about this. One interesting feature of this is that this actually organizes various dimensions in multiplets or sequences, if you like. So the idea is that if you want to seek in dimension D, you calculate this number, take the square-free part, and that determines a real quadratic field you're going to use. And this number D is then used to specify precisely what Ray class field over this real quadratic field you're going to use. So you can turn this equation around. So here's an arbitrary square factor. And then you can regard this as a Diophantine equation. So you specify the real quadratic field by specifying the capital D, and then you calculate in what dimensions does the Sic use that real quadratic field. And the general solution of this equation is known. It's an infinite sequence of dimensions given in terms of something which is called the fundamental unit of norm, positive norm in the real quadratic field. I'm not really going to go into what this is, but this is something quite simple that you can look up in Hardy and Wright or whatever. So this is an infinite sequence of dimensions which are number theoretically connected. So you specify an integer D to specify a real quadratic field. You find the fundamental unit, etc. And then you stick it into this formula and get an infinite sequence of dimensions. In this case, if capital D is 5, it's 4, 8, 19, 48, 124, etc. And I've written down only dimensions where Sics are known to exist. Actually, the last one here is only known numerically. The others are known exactly. Here's another sequence that I'm very fond of. There's more to it than that because the symmetry of the Ray class Sics in these dimensions grow in a predictable way in such sequences. This is at least partly, this can be derived from the number theory behind it. Anyway, these are the special sequences that Scott and Russell found. They occur in these sequences. So this is sort of nice. And you can see what the dream is now. Could you perhaps prove inductively that Sics exist? Suppose you could produce an argument saying that if a Sic exists somewhere in the sequence, it has to exist in all the other entries too. That would be a dream. Maybe one has to refine that a little. So I should say a little bit about I wonder how, I don't know how to get rid of this green thing. I apologize. So I should say a little bit more about the conductor, which is on one hand simply the dimension in Hilbert space in which the Sic lives, but it's also something which precisely specifies the ray class field. And a basic fact about this conductor is that if you have two ray class fields over the same base field, but with different conductors, D1 and D2, then the ray class field with conductor D1 is a subfield of the one with conductor D2, if and only if D1 divides D2. So if you look a little bit in more details, the sequence I presented, so 4, 8, 19, 48, 124, etc., you find that 4 divides 8, divides 48, divides 2208. So the Sic here uses a subfield of the Sic here, which uses a subfield of the Sic here, etc. 4 also divides 124, so the Sic here uses a field which contains this field, etc. This sits on the side because 4 doesn't divide 19. So what I've done here is that I've divided up the sequence into a lattice, where the links here tell you whether a given ray class field is contained in one above. And that perhaps suggests that an inductive existence proof should concentrate on one of those subsequences. The subsequences that I've sort of drawn as vertical lines here are very easy to find. So if you start in dimension D, 4 say, and then you replace D by D times D minus 2. Then what happens to this thing here, which determines the real quadratic field, is that D plus 1 D minus 3 goes over into this, and this is a square, so it doesn't affect the real quadratic field. In other words, the square-free part remains unchanged. So there are infinite sequences of dimensions in every case, such that if you do this replacement, clearly this thing, clearly this divides that. So that this gives rise to infinite subsequences, where this is a subfield of, etc. There is more to this than that, because once you start looking carefully at the Sics in such a sequence, it seems to be the case, and it's been verified in some 20 cases where we had the high-dimensional Sics available, that there are definite geometrical properties of the Sic in the higher dimension that you can calculate in a simple way from the Sic in the lower dimension. In the interests of giving a reasonably short talk, I wasn't going to give much detail about that. And perhaps the most important thing is we can only do this partially. We're probably not very close from actually calculating the Sic in the high dimension from the Sic in the low dimension. But there is enough stuff there to make one suspect that a sufficiently clever person could do that. Okay, so these are these sequences of dimensions which are connected by having Sics from this that use the same base field. There's another sequence that I'm particularly interested in at the moment. So if you look up again in Hardy and Wright, read about real quadratic fields. I mentioned that I used the fundamental unit of positive norm to calculate calculate the dimension. But in some cases, there also exist fundamental units of negative norm. If you have this relation between capital D, the base field, and the dimension here, the conductor, then this happens precisely when D is n squared plus 3. So this gives a sequence of dimensions where the base fields are changing, but where some geometrical properties are actually the same. This somewhat obscure number theoretical property actually is reflected in the fact that in these very dimensions, the most symmetric Sic, the ray class Sic, always has anti-unitary symmetry. And there are some interesting things here. So I was going to show you again. So this thing I showed you before in dimension 28, we were finally able to get that into a paper as follows by simplifying the thing a bit. So if I show it like this. So this is what that very same solution looks like if I apply a few tricks that we have learned since the first time we found it. So here's 28 components in the fiducial vector in dimension 28. And there are similar things to be said about all the Sics in all the throughout this sequence I described. So first of all, I've used this property that 28 is 4 times 7. So I have expressed things as a tensor product, 4 times 7. And then I have carefully selected my fiducial vector so that it talks to the symmetry. So actually there are only altogether 8. There are some zeros, so there are actually only 8 independent numbers in it. Each one occurs 3 times because of this order 3 soundness symmetry. And more importantly, the individual numbers aren't too bad either. Because, and I should say that the fact that this possibility exists was first noted by Marcus Grassel. So what Marcus noticed was that in certain dimensions, and in particular in this sequence, you don't need the full ray class field to express the Sic. This whole thing, if you ignore this, this phase factor here, which comes from dimension 4, I could remove that if I wanted to. But apart from that, these numbers require a number field not of degree 576 as we had before, but it's 2 times 2 times 3 because this is cubic times 2 again. So it's the number field you need to express the fiducial has only degree 24. And this is somewhat interesting because the ray class field that is relevant here, the base field is actually Q over square root of 29. The conductor is 28. And we need the full ray class field.
I think there's a question from the audience. Sorry.
A question. Then the question is if I can localize the question. Can I? How do I find the question?
Okay, the person is supposed to ask it.
That's reasonable, yes.
Okay, let's wait. Okay, maybe, okay, seems like it's not the case. Okay, sorry for interrupting.
Okay. What I was saying was that you don't need the full ray class field to express the Sic fiducial. You do need the full ray class field to express the Sic, because the Sic involves also the, you have to act on this thing with the Weil-Heisenberg group. The Weil-Heisenberg group contains the relevant root of unity. To express the relevant root of unity, you have a subfield of this ray class field, which involves the cyclotomic field, which is, say, the old boring part. The part that stands here is the interesting part of the ray class field, the part that you need to add to the cyclotomic field in order to get this mysterious ray class field. And that's all you need to express the Sic. So it looks a lot simpler than it used to. And I'm very pleased with that. So I guess this is the only formula that I'm really going to show. I should also tell you what I hope to do next. I hope to do the following. So my hope is that I will be able to solve exactly for the Sics with some closed formula in one of these sequences, one of these infinite sequences. I don't particularly care which. I want to go to heaven, but I don't care what ladder I'm using. After that, I want to solve basically Hilbert, well, not the entire Hilbert's 12th problem, but the significant part of it. And finally, and I'm probably putting this in so to say, increasing order of difficulty, then I would like to find a role for these sequences in physics. I have no idea what this means, But I like to think that when whoever it was, probably Catan, first worked out the representations of SU3, etc., he found these sequences 3, 8, 10, etc. I don't think anyone had any suggestion that this would have to do with physics, but we know it has. So maybe there is something to this point here, but it will be very difficult. This one might be easier, and this one might be easier, but I'm not anywhere close to it, of course, and probably nobody else is either. But we'll see. And I will end by showing a few references. All of these papers are very good, and I've enjoyed them hugely, and I think you would enjoy them too if you have a look. There are various aspects of Sics that I didn't at all touch here. You heard about some of them from John yesterday, yeah, this was what I intended to say. And it actually went quite quickly, didn't it? Quicker than a whiteboard talk, actually, which is...
Thank you very much, Ingemar. Do we have any questions?
So Robert is here. If I may ask a question quickly. So the very last point you're referring to John's talk yesterday. And I mean, he is connecting Sics to Wigner functions.
Mm-hmm.
So here you would have a physics connection. I mean,
sorry?
In your program slide, you the last point you wanted to find applications of Sics in physics, and so here someone brings in a Wigner function. What is your perspective on that?
Well, you see, what I want, and I don't think John particularly cares, I want to find a role for these sequences in physics.
Mm-hmm. Oh, I see.
4, 8, 19, 48, etc. I'd like these things to come into physics. I'm very happy that other people try to take physics in different ways. I'm very happy about that. But I would like to make this kind of connection. I don't think, you have to ask him, but I don't think John is particularly aiming for that.
Okay, thank you for the clarification.
Maybe his program is a lot more reasonable than this one, but...
Other questions? We have something in Q&A. Should I read it out? Because I'm...
there's a question which actually I can answer. In the sequence D4, 8, 48, etc. up to 2208, is there an exact seq known for D equals 2208? The day before yesterday, when I asked Marcus Grassel about it, the answer was no. The world record is still 1299, which is the third entry in the sequence above 12. And yeah.
Okay. So we have, yeah.
I mean, these things are, I mean, even if they are in some sense simple, 2208 components aren't all that easy to work with. I once tried to work with dimension 1155 and I had to reinstall Mathematica because it collapsed.
Okay. Other questions? Well, if I could ask a kind of vague question, do you have an idea of what kind of connection to physics there might be in such sequences of numbers?
No, No, I was explicitly saying, wasn't I, that I think these questions are in increasing order of difficulty.
Sure.
And I'm not so sure that I'll ever get to the first one. So no, sorry.
Okay.
But there should be something.
Yeah.
Can I ask you something about a question about early in your talk about the Clifford group in even dimension? So you had a formula there, I believe, where you were conjugating Pauli operators under Cliffords, and you were permuting the Paulis without changing the sign. Can you just?
I'll go back to that side, but I just like to point out that this paper here by Andersson and Dumitru is actually an interesting paper about even dimensions. And now I'll try to find the slide where I discussed this. Why did I do that? Here, right?
Let's see. Yeah, the formula at the bottom of the slide.
Yeah. And this is badly organized, I apologize. As says, it contains a copy of the symplectic group SL2 and then the integers modulo D bar. And D bar was defined on the next slide as being equal to D if D is odd and equals to 2D if D is even. I don't know if that helps.
Okay, so let me ask in this way, and also I understand now that you are thinking of a kind of single copies of the Clifford group, not like multiple qubits and so on and so forth. But for the cases that you consider, I mean, you can always write the Clifford group as some sort of product between the symplectic group and the Pauli group. And sometimes this product is a semi-direct product, but sometimes it is not.
Right.
It is our understanding. And what do you say about this product, if anything?
Yeah. If the dimension is odd, the story is fairly straightforward.
Then
if you
yes,
mod out the center, so you ignore phase factors, you look at projectively, then it's a semi-direct product. If the dimension is even, things do become a bit more complicated in a funny way, because there are certain elements in the Weil-Heisenberg group that are actually also in the symplectic group. There are 8 such elements. And this messes things up, so there is no simple way to describe it.
Okay.
It's simply messed up a bit. And it's also interesting that in the odd case, it's known how to write down a faithful representation, phase factors all coming out correctly in the odd case for the Clifford group. In the even dimensional case, no such thing is known. And I have even proved that it's impossible, but I didn't publish it because perhaps I made a mistake. I often do. But I think that a faithful representation of the Clifford group isn't really possible in even dimensions. That's another complication. And this all has to do, now I define things by enlarging the center in the even case. You might think that maybe that's a problem. I shouldn't do that. But actually this makes perfect sense from the point of number theory, because the thing is, the cyclotomic field, you use a d root of unity. If d is odd, the 2d root of unity gives the same cyclotomic field. So what we gain by introducing this enlarged center is that we get a one-to-one correspondence between the Weil-Heisenberg groups and the cyclotomic fields. And from the point of view of what happens later, this sounds exactly right. Oh, and there was another thing that I didn't even mention. So I said that the dimension is a conductor of the ray class field. That's true in the odd case. If the dimension is even, if d is even, it's actually 2 times d, which is the conductor of the relevant ray class field. So this doubling goes on in the even dimensions. And as I was saying, I think, I don't think the last word on this has been said. I think there's room for someone writing a clarifying, probably rather long paper where he or she explains everything. I don't think this has been done yet.
Mm-hmm. Yeah. Good. Thank you. Thank you.
Okay. Any other questions? I don't see anything. Johan, should we maybe adjourn to the sort of meeting room at this point so people can?
Yes, we can. So we can conclude the sessions. Sure. Let me stop the video.